split into its ions, and that means that it has charges and they're going to be aqueous. So this is our left, this is our right. Our left is going to be our solid side. We say it's undissolved, meaning it doesn't have any water in it, okay? The right is the dissolved side. It's going to be aqueous, it has water in it, and so on. Remember, if we have a really big K, this you might not remember, but a big K means it lies right, and a little k means it lies left. So if our KSP is a really big number, greater than 1, remember that, greater than 1, that means it's going to dissolve very easily. I add water to it, I don't have to do anything, it just dissolves. Salt has a really big K. If it has a really little K, that means even if I add water to it, it doesn't dissolve. We call that insoluble, okay? So like our crystal violet, that doesn't dissolve. I have to like heat it and stir it for days to get it to dissolve. It just has a really little K. I got to shift that equilibrium to the right. So the left side is when our K is less than 1. Remember, that just means less than 0.1, and our K is greater than 10. SP stands for solubility product, but it's going to be the same thing. Our products over our reactants, any coefficients become exponents. Pure solids and liquids do not go in. Pure solids and liquids do not go in. So these never have a bottom. So these KSPs never have a bottom because the left is always a pure solid. Okay, just real quick, One Direction's going to sing to you. Talk about everything on the slide, left, right, how come pure solids don't go in and they don't have bottoms. Ready, go. Okay, let's do calcium phosphate. Phosphate is -3, calcium is +2. So we have that going on. I would prefer that you don't get out your ion periodic table and you start using the group numbers for charges. You just like won't have an ion periodic table on the exam, and it's good to start weaning yourself off of it. Common ions are always on that poster. You don't have to memorize those for the AP exam. They will have them somewhere for you. So just for now, but you will have to memorize the charges that way. So go ahead with your battle buddy. Go ahead and write your equilibrium expression. Make sure you balance your equation, and then make sure you, and then after that, can you write your KSP? Our coefficients become exponents. And remember, pure solids and pure liquids. So you have something cubed and you have something squared. We'll do a sample problem, but this might require to use a cubed root when we solve for it. So we'll practice making sure you just remember where that button is on your calculator. But just don't forget that that 3 goes here, that 2 goes here. Okay? And that we got these from balancing our equations for the charges. There's a vocab word that's like super, super imperative to solving these, and it's called the solubility. Solubility is like a synonym for dissolving. If something is soluble, it dissolves. Solubility, if it has a lot of solubility, that means it dissolves very easy. If it has low solubility, that means that it's going to lie left. It does not dissolve. Okay? It's not the same as KSP. The words they're going to say is molar solubility. In molar solubility, is X. When we do like an ice table and you know how we have to like figure out how to solve for X, molar solubility is the words for X. So when we do our KSP and we're solving for X, well, we're actually doing the solving for molar solubility. It's going to be in moles per liter, which is molarity. One last thing is something called the common ion effect. So let's do our NaCl again. And we're going to pretend we're going to add silver chloride to it. So in our beaker, we have our sodium ions and our chloride ions. Because the water molecules are like little magnets, it separates it all out into their ions. The real word for that is dissociation. And then let's say I added in a bunch of AgCl. That means same game, they were separated into their ions. So what I did is I added in a bunch of Ag ions and Cl minus ions. What I really did is I increased my concentration of chloride ions. There's more of them in there now. That's called a common ion. Common just means they're the same. Ion just means that they have a charge to it. If I increase my concentration of my chloride, it'd be like if I squirted a bunch more into the right. And if I squirted a bunch more into the right, which way is it going to shift? Tell somebody next to you, where is it going? Left, right? Because I have more on this side, so it's going to shift left. But now the left is the powder side. Okay? So what does adding a common ion shifts left? To the undissolved side. The left is the solid side. It's the powder side. It's the dry side. If we shift it to the powder side, it is undissolved. Remember, dissolved and solubility are the same thing. We're reducing solubility. So adding a common ion is going to shift it left, which always reduces solubility. When Archie's going to sing to you, can you please explain that to somebody and then let them explain it to you? Everybody has to say it. Ready, go. These are the words. Write the equation for the dissociation of calcium chloride and water to your solid double arrow aqueous. Okay, so go ahead and do that. Biggest thing is just looking up the charges or remembering the charges. Remember that the solid is always going to stay on the left, no matter what it says. Put your solid on the left. And then it splits into its ions, so you've got to have charges for that. And it has to be balanced. So anything on the left is aqueous, and then just remember to go back and balance it to make sure everything is balanced. So that means that the powder is going to split into 1 calcium and 2 fluoride ions. For our eyeballs, it'll look like it just dissolved. If you're writing our equilibrium constant expression, our equilibrium constant is K. SP stands for solubility product. That's just when we're dissolving stuff. We take our products over our reactants. Our coefficients become exponents. That's why it's really important to balance them. And none of these are going to have bottoms because pure solids don't go in. Okay? So let's take a look at the math. It says the molar solubility. So this is going to be X in our ice table. I am going to start weaning you off of ice tables. They become cumbersome the harder the stuff gets. And so like starting tomorrow, it's like you might not want to do them anymore because it just kind of creates extra work. Like if you understand equilibrium and shifting and X's and stuff, I don't think you'll need it. I'm going to do it one more time here, but then I'm probably not going to do it again. The molar solubility of the calcium fluoride is 2.1 times 10 to the 4. That means it's X. That's what the words mean. We're always going to get a temperature because we know a temperature can change K. And we're going to calculate the KSP. I'm going to go ahead and write my ice table for you one time just to remind you of where the X's come from. But after this, I'm pretty much not going to do it. Pure solids don't go in, so I'm not going to even have anything on my left. I'm going to start with nothing at time 0. That's going to be a plus 1x. This is going to be a plus 2x shift, right? So that's x and 2x. I got to start writing 4. So my KSP equation, remember, is up here. It's my calcium, which is my X, times my fluorine, which is my 2X, and that gets squared. Right? So it like feels a little redundant because this 2 is because of this 2, but that's also because of that 2. And it all kind of has to fit together. Okay? And if we know what X is, we can just plug it in. That's all we're going to do. I like to like go 2.1 times 10 to the negative 4 and store it as X, and then just use my parentheses really well. If you don't use your parentheses, you got to do it really carefully because 2x quantity squared is actually 4x squared. So go ahead and plug that in for X. And I know I have the wrong answer, so somebody's going to tell me. I think it's 3.1 times 10 to the negative 11 or something. 3.7 times 10 to the negative 11. If you didn't get that, go back and double check your parentheses. Because 2x quantity squared is not the same thing as 2x squared. It's actually 4x squared, because 2 squared is 4. You always follow it up like this. That's a little k. That means it does not dissolve very well. It lies left. It lies on the powder side. Even if I add water to it, it's just going to be like powder at the bottom of the water. Okay? Now for letter C, we have to explain why if I added barium fluoride. Barium's plus 2, fluorine's minus 2. So if I add barium fluoride, I'm really adding a bunch of extra fluoride ions. Here's my common ion. The bariums are just spectators. They're not going to do anything. But the common ion, we know from Le Chatelier, the common ion, if I add more of my concentration of my right, it's going to shift it to the other side. It's got to balance it back out. So adding more fluoride ions will shift the equilibrium left. to undissolved. The left is the powder side, not the dissolved side. When things aren't dissolved, we say it has a low solubility, so it reduces solubility. Like it turns it from liquid to crystals. That's what those borax ornaments are. I force it right when I heat it up, and when it cools down, it shifts back to the solid side and makes those crystals. Okay, see if you can go ahead and do number 2 with your battle buddy. Maybe scooch a desk so you can talk it out. Ready, go.